You lean into the throttle, the motor hums, and the scooter accelerates right up to 25 kilometers per hour. And then you hit a sudden wall. The motor pulls back its power, coasting along while you feel the machine actively resisting its own momentum. Hidden inside the deck of a modern Ninebot scooter is a 36-volt battery and a motor that can easily push a rider to 35 kilometers per hour. Mechanically, the hardware is ready to go faster, but it is deliberately restrained. When Segway built its first personal transporters, they were pitched in indoor showrooms as pedestrian alternatives. They were slow, bulky, and designed to share the sidewalk with people walking. Today, riders want to keep pace with city traffic. To bridge that gap without getting banned from city streets, manufacturers implemented a digital governor. The 25 km/h limit allows these scooters to satisfy strict regional laws and avoid localized traffic enforcement. The hardware is highly capable. The barrier keeping a rider from hitting top speed is entirely political, enforced by lines of code. Companies like Segway Ninebot actively monitor how users interact with their software. When riders find a way to bypass the speed limit, the manufacturer pushes over-the-air firmware updates, specifically versions 1.7 and beyond, to patch those vulnerabilities. Because of these rolling patches, there is no longer a single button a user can press to unlock maximum speed. The required method depends entirely on the specific firmware version and the hardware generation sitting inside the deck. Unlocking a scooter has transitioned from a simple software trick into a technical diagnostic contest between factory updates and owner ingenuity. The first and most frictionless method of unlocking speed relies entirely on Bluetooth. Using mobile apps like ScooterHacking Utility or XiaoDash, a rider can communicate directly with the scooter's dashboard. This approach comes with a strict prerequisite. It only works if the scooter's motor controller is running an older firmware version, specifically DRV 1.7.3 or below. If the scooter meets that condition, the app can rewrite the machine's regional serial number. By changing an EU prefix like 02GV to a global prefix like 01GX, the software identity of the vehicle is altered. This simple string of text tricks the scooter's brain into adopting American speed limits. The 35 km/h cap is instantly unlocked without the rider ever touching a screwdriver. While this method represents the most accessible form of hacking, manufacturer crackdowns are rapidly making it obsolete. As the software loophole closes, riders are forced to escalate their tactics. For updated scooters locked out of Bluetooth hacks, the next tier of modification bypasses the software firewall entirely using a physical speed release cable. This requires opening the scooter's stem and plugging a third-party cable directly into the wiring harness, placing it exactly between the handlebar interface and the motor controller. It successfully overrides the speed limit, but it comes with an operational trade-off. The rider loses the ability to connect to custom apps to fine-tune their acceleration curves or adjust their brake settings. This is a brute force hardware workaround used to solve a software lockdown. It represents the first major step away from how the vehicle was engineered to operate. The newest, most heavily encrypted scooters, like the Ninebot G2 running firmware version 1.7 or higher, require a final resort, the ST-Link hardware flash. This method demands opening the bottom deck, exposing the controller, and manually injecting custom firmware directly into the machine's memory. The user connects a programmer tool to 3 specific test pads on the circuit board: ground, the clock line, and the data input-output line. This bypasses the locked Bluetooth module. They inject new code down the data line, entirely rewriting the core operating system. The performance rewards of this complex procedure are massive. The rider gains granular control over the motor, allowing them to adjust field weakening, dictate exact power curves, and calibrate regenerative braking. ST-Link flashing is the ultimate escalation in this process. By rewriting the machine's brain at the physical level, the user achieves total ownership and maximum performance. Once the code is rewritten, the rider can effortlessly cruise at 35 km/h. Their commute is now shorter, and the scooter can finally keep pace with city traffic. But bypassing the factory efficiency limits comes with a hidden energy cost. Pushing the motor beyond its designated parameters causes severe and rapid battery drain. The hack also introduces severe mechanical stress. As the copper coils heat up inside the motor, thermal buildup threatens the electronics, while the higher top speed places an extreme load on the stock braking system. Unlocking the speed limit inherently violates the strict physical tolerances the scooter was engineered for. The rider, effectively, becomes a test pilot for their own modifications. The financial risks are permanent. Hacking the controller instantly voids the manufacturer warranty, and a single mistake during a firmware flash can permanently brick a $1,000 machine. This stands in sharp contrast to compliant scooters meant for the general public, which remain locked down, heavily regulated, and predictable by design. By stripping away the digital governor and modifying the firmware, the rider assumes all legal and physical liability that the manufacturer previously held. Bypassing the code to hit 35 kilometers per hour means accepting full responsibility for the physical and financial consequences that follow.